use it a lot, so it's kind of foreign to us. It's called radians. So let me first tell you what a radian is. So when you open up an angle, and this is like a rotation diagram, and here's your initial ray, opening up in that direction to a terminal ray, okay? When the length of this arc is finally the exact same as the length of your rays, then that's 1 radian. So if this were 10 inches and this is 10 inches, then that's 1 radian. So your radian measure, which is a Greek letter they won't use X, they'll use a Greek letter like this one's theta. That number of radians is equivalent to whatever the arc length is. So S stands for arc length. Over R, and this R is like a radius because it's almost like you're opening up a circle. So when those two are equal, that ratio will be 1, and therefore this angle is 1 radian. If you continue to open up, the arc length grows, obviously. The R always stays the same. So if we continue to open it up, and that arc length became double the length of the radius, so let's say once it got opened up over here, and that was double the size of your radius, then the ratio would be 2 to 1, and that angle would be 2 radians. Does this make sense? Okie doke. So a rearranged version of this formula that you'll probably use more often is, because it's easier to remember, is that S equals theta times R. So your arc length equals your angle measure, which has to be in radians. You can't plug a degree measure into this formula. It has to be a radian measure times the radius. And that's easier to remember because you'll just hear me refer to that as the SOR formula. So the SOR formula gives you the arc length is equal to the radian measure of the angle times the radius. Okie doke? Okay? So we'll use this version right now because we're trying to find the angle measure in this section. But what is the angle measure in degrees? If I were to open something up, pretty much a half circle, what is that angle measure? 180. So we all are familiar with that in degrees. Now we're going to see what 180 degrees is equivalent to how many radians. So 180 degrees is equivalent to some number of radians that we'll get to. And we'll get to it using our formula. So if I wanted my number of radians, that would be theta. What is my arc length here? The arc length here is equivalent to the what of the circle? Like, what is this distance around a circle referred to? The circumference. But this is only half of the circumference, right? Do you guys know the circumference formula? Pi d or 2 pi r. And we'll use 2 pi r because we have r's happening here. So your arc length of a full circumference would be 2 pi r, but this is only a half a circle, right? So that would just be 1 pi r. Do you follow that? So your arc length, this S, is 1 pi r over r. And they don't tell you what r is, it's just however big this radius is. But and the r's therefore cancel. Yes? So that angle measure reduces to pi. So a very important takeaway here is that 180 degrees in the degree world is like pi radians. And how many radians is that? What is pi? What number is pi? 3.14 radians. So just for you to remember, that was a half circumference up top, 1 pi r over r, and it told us that that angle measure was pi radians. So knowing that it's 180 degrees, those are equivalent. Just like 0 degrees Celsius is equivalent to 32 degrees Fahrenheit, right? Totally different numbers, but they're the same thing because they're in different units. Over here, we're talking about a full circle now, right? How many degrees do you know is a full circle? 360 degrees. So we're going to figure out how many radians that is by doing, again, the number of radians, theta, equals the arc length, which is a full circumference now, 2 pi r, over r. Your r's cancel, and that's 2 pi radians. 360 degrees is 2 pi radians, which is approximately 6.28 radians. So where would 1 radian be? If this is 3.14, when you open this up, oh, here it is. I was going to say, I really liked my tool that I was using the other day. If this is 3.14 radians, where would be 1 approximately? This is 0 radians. 0 degrees and 0 radians do line up. And then you open up to 3.14. So what quadrant would 1 radian be in? It's not quite 45 degrees, but one. It's quadrant 1. It's not a 45-degree angle, but this is all proportional. So you could do like pi radians. Whoops, I'm running out of lead. Pi radians is to 180 degrees, as 1 radian is to x degrees. It's all proportional. So you could cross multiply, you'd get pi x equals 180 degrees. Divide both sides by pi, and x equals whatever 180 divided by pi is, 57.3-ish. So a little more than 45. So 1 radian is approximately 57 degrees. You're never going to really have to know that, but you should know where, like, because sometimes people get in this zone where they're like, well, 1 radian, that's right here. No, that's 1 pi radians, which is technically 3.14 radians. So 1 radian is back here in your first quadrant. So you have 0 radians, 1 radians, 2 radians is somewhere over there, and then 3.14 radians. Does that make sense? Okay, so that's what a radian is. When we get through this chapter, a lot of what we do will be in radians, so you have to be familiar with that. All right, example A here. Determine the number of radians that the minute hand of a clock passes through if it has a length of 5 and its tip travels a total distance of 13 inches. So this is just, if you give yourself a picture, the minute hand has a length of 5, and it's going to travel, its tip is going to travel a total distance of 13. And then this is obviously going to still be 5, right? The length of the minute hand. This is just your SOAR formula. So what do we plug in for S? What is our arc length? 13. What is our angle measure in radians? I don't know, so I'm going to keep that theta. And what is our R? 5. So you just divide both sides by 5, and theta equals 2.6 radians. We don't have to write radians every time. If you don't see a degree symbol, assume it's in radians. Okay? If we jump to 4 and we're converting each of the following angles in degrees into radians, you can do, if you want, you can do a proportion. So we could say 90 degrees is to 360 degrees, as how many radians is to, what's the equivalent of 360 degrees in radians? 2 pi. You can do it like that and cross multiply. Or, do you remember dimensional analysis? Does that sound familiar? Kind of, but this won't be that bad. Dimensional analysis, just like rationalizing anything else, it's a way of changing the appearance of something without changing the value. So we're going to change the appearance of 90 degrees into radians without changing the value. So in order to not change the value of something, you have to multiply by 1, right? But you're going to creatively multiply by 1. You want your degrees to cancel. So I'm going to put 180 degrees in the bottom, and I'm using 180 because I know how many radians is 180 degrees. Pi, or 3.14, but use pi because it's exact and 3.14 is technically rounded. Pi radians over 180 degrees is the same thing, so it's multiplying by 1. It's something over itself. So it's multiplying by 1, but it's going to change the appearance so that your degrees will cancel. And that's how I know to put degrees on the denominator, because it started in degrees and I want the degrees to cancel. And it'll be 90 pi over 180. And 90 over 180 reduces to 1/2, right? So pi over 2. You probably won't use the proportion way, but it's an option. Okay, so to get out of degrees, multiply by pi over 180. Pi radians over 180 degrees. That's just the rule. Multiply by pi over 180 and reduce. So this will be 120 pi over 180. Your 120 over your 180 will reduce to 2/3. So 2 pi over 3. And that's in radians. Good? So on the flip of that, if you want to go from radians back to degrees, which I think is what we'll be asked to do on the back. These are all currently in radians. We want to go back to degrees. So we're going to multiply by 1, but we're going to put the degrees on top and the pi radians on the bottom. So again, we're multiplying by something over itself. We're not changing the value, but this will change the appearance. When you do this multiplication, your pi's cancel, yes? And rather than actually multiplying 5 times 180 and getting a huge number, we can reduce things first. 180 and 6 reduces to 30 and 1. So on your numerator, you end up with 5 times 30, which is 150, over 1 on your denominator. So that's 150 degrees. Which should make sense because this radian measure was 5/6 of pi. So if pi is a half circle, 5/6 of the way there puts you somewhere over there, doesn't it? Right? 5/6 of pi. That's 5/6 of the way to a half circle. So that angle's somewhere over there. And because we think in degrees a little bit more fluently right now, if this is 180, it makes sense that that's slightly before 180 at 150. Does that make sense? For this one, again, you'd multiply by 180 over pi. Your pi's will cancel. Your 180 over 2 becomes 90 over 1, technically. And 3 times 90 up top gives you 270 degrees. 3/2 of pi is like 1.5 pi. So if you were opening up there's 1 pi, and another half of a pi, that would be right there, yes? And we all should be able to agree that that's 270 degrees. 0, 90, 180, 270. So it does make sense. And now this is 3/4 of pi. So before we actually do it, here's 1 full pi, right? We want to go 3/4 of the way there, which is going to be perfectly halfway through the second quadrant. Yes? What angle in degrees would you guess that is before we do the conversion the long way? What, if this is 0 degrees, this is 90 degrees, and that's 180 degrees, what's perfectly halfway between 90 and 180? 135 would be perfectly halfway in between. And that's 3/4 of the way from 0 to pi, correct? So it should work out to be 135. If you're thinking logically, if you just check it, multiply by 180 over pi, your pi's cancel, your 180 and your 4 become 45 and 1, and 45 times 3 is 135 degrees. So I do think it's helpful to logically make sense of it and think about how that works out, and should kind of, connect the puzzle pieces a little bit. But obviously there's a way where you could not understand anything and just memorize multiply by 180 over pi or multiply by pi over 180 to convert. Okie doke. These are still radians. They're telling us they are, but they're radian measures that don't involve pi. Just out of curiosity, whereabouts do you think 5.8 would go? Radians. Here's 0 radians. How many radians is this? 3.14, otherwise known as pi. So there's 3.14. So what's halfway between 0 and 3.14? 3.14 divided by 2. That would be 1.57. So add on another 1.57 to 3.14, and that would put this at 4.71 before we get back to 6.28. So where would 5.8 be? Fourth quadrant, right? Somewhere down in here, somewhere between. You'd open up from 0 past the 4.71 to 5.8-ish. Yes? And I'm going to remind you of reference angles. If this is where 5.8 would land, your reference angle is right here, correct? It's the difference between your terminal ray and the x-axis. So the difference between 5.8 and 6.28 would give you your reference angle. And we will have to do that for radians as well, but we're not quite there yet. So anyway, the conversion, even though these don't have a pi involved, you still do 180 divided by pi. And then you just type it into your calculator. 5.8 times 180 divided by pi. And that's a 332-ish degree angle. So approximately 332 degrees, which should make sense because we're in the fourth quadrant, right? We're just shy of 360. So you'll do those conversions the same way. Okay? And then in the very last section, this is where we do, and I'm going to use this up here as my guide. What quadrant, Jason, would 2 radians be in? If you were looking at this, 0 opening up to 6.28, where would 2 radians be? First, second, third, or fourth? Nope. The first is anywhere from 0 to 1.57. And then 1.57 to 3.14 puts you in the second. And then between these two numbers is the third, and between these two numbers is the fourth. So where does 2 fall? Say it again. Between 4.7 and 6? 2 is not between 4.7 and 6. Second. 2 is between these two numbers, yes? So we'd open up to 1.57, and then we'd go a little bit further to 2 radians. And your reference angle would be right here, right? The terminal ray to the closest x-axis. And that we know is 3.14. So what is the difference between 2 and 3.14? 1.14. So your reference angle would be 1.14 radians. If I went -1, so if I go in the negative direction, this is -1.57, right? So here's 0. Here's -1.57. So I've already passed -1, yes? So -1 in my rotation diagram has me opening that way. That would be a -1 reference angle, or -1 angle location. How far away is that from 0? 1 radian, right? Remember, reference angles always have to be positive. So your reference angle would equal 1 radian. And then let's just jump to that last one, 6.3. What's a full circle again? 6.28. So if I go around 6.28, I have to go an additional, how much? 0.02. Very good. So 6.28 is here, and I'm at 6.3. So my reference angle, that's 6.28. My reference angle is 0.02 radians. Good? Any questions? So your homework coming up, and then just your test corrections also due. Okay, good. And George, you can throw yours up too. Yeah, okay, perfect. Thank you. Bella and Chris Brooks, I want to talk to you two for a second. And then Faye and Georgia, you two.